welcome to today's technical webinar as part of our series. I'm your host, Jessica Bennett. We're very excited for today's webinar that will be presented by Ron Kravchuk and Dr. Glenn Ulrich on risk-based and biotechnology alternatives to address natural gas emissions from leaking oil and gas wells and other methane sources. A few housekeeping items up front. We'll be keeping all phone lines muted during the presentation to limit background noise. If you have any questions throughout the presentation or at the end, you can enter them into the chat and we'll read them at the end, or you can ask them live during the Q&A session by raising your hand and then we will unmute your phone line. This webinar has been approved for 1 PDH credit. If you would like to receive credit, you can click on the link in the chat to download the form, complete it, and return to us. If you have any issues accessing that link or downloading the form, you can also send us an email at daniela.savin@parsons.com to get a copy of that form as well. There are 4 questions that are multiple choice that you have to answer to get credit. I just posted those in the chat and I will post them again throughout the webinar so you have access to those if you have any problems downloading the form. And finally, this webinar is being recorded and will be posted on our YouTube channel in the next few days. So a brief overview and agenda for today's presentation. I'll introduce the speakers and Ron will give the core value moment before getting into the technical presentation that's broken into a few different sections. And finally, we'll have Q&A at the end. So Ron has over 16 years of experience in the oil and gas industry at Parsons, and this includes everything within plugging and abandoned operations of early era oil and gas wells, including risk analysis, bioremediation, hydrogeological investigations, permitting, and many more. He holds a Bachelor of Science in Mechanical Engineering from Saginaw Valley State University. Dr. Ulrich has a Bachelor of Science in Microbiology and a PhD in Microbial Ecology with over 25 years of total experience. He's a technical director with Parsons, specializing in developing and applying sustainable biotechnologies for the oil and gas and environmental remediation industries. He has previously served as a lead scientist for an oil and gas exploration and production company. And with that, I'll turn it over to Ron for the core value.
Thank you very much for the introduction, Jessica. Parsons holds 6 key core values, which are safety, quality, diversity, innovation, and sustainability. Today, we are going to focus on sustainability and safety for our core value moment. With over 900,000 orphan wells, even with a large influx of bipartisan infrastructure law funds, there won't be enough to address them all. Sustainable and efficient approaches are key to making the funds stretch the farthest by reducing waste and diverting crude impacted soils from landfills can yield significant cost savings. Bioremediation can quickly and quite effectively eliminate petroleum impacts where soil conditions are feasible, and economies of scale can be realized looking at large amounts of orphan wells through a programmatic approach, utilizing risk analysis and management to triage wells with the greatest environmental risk. When it comes to safety, historically oil and gas drilling is a dangerous and incident fraught occupation. Using modern health and safety management techniques, field leadership, and training partnerships with contractors, we can mitigate and eliminate most hazards while building a strong safety culture. Using these techniques, Parsons Mid-Michigan Oilfield Restoration Project has accumulated a combined 1.6 million safe work hours, and personnel have driven 1.5 million safe miles spanning over a decade. In this split image, you can see a historical 1952 aerial of an active oil field on the left and the present day aerial image on the right. There are over 35 wells along with dozens of associated production facilities within this square half-mile view alone. So why do orphan and abandoned wells matter? There are over 3 to 4 million orphan and abandoned wells between the US and Canada. Many of these are undocumented or were drilled before permitting and records keeping began. Approximately 900,000 are orphaned, meaning there is no viable responsible party. Therefore, the care reverts to the state or federal governments. Of these 3 to 4 million, over 20%, or approximately 800,000, are estimated to be leaking methane, oil, and/or brine. As you can see, the distribution of known U.S. orphan wells on the map below, with the bulk between the south central oil states and up through Appalachia. Roughly $4.7 billion was included in the bipartisan infrastructure law to address orphan wells over the next 10 years. The funding will predominantly go to the 26 states in dark blue on the map. State grants include initial grants, formula grants, and performance grants with varying timeframes and amounts per state, and much smaller amounts for federal and tribal activities. Parsons has been providing solutions to oil and gas clients and governmental agencies for 60 years. Currently, we have addressed over 1,800 well sites that have been prioritized, plugged, and restored. We are continuously innovating to find efficiencies, risk-based solutions, and minimally invasive investigation techniques. Essential to prioritization of wells is performing a risk analysis that looks at many factors of a well. When doing a risk analysis, the initial drilling and construction of the well can make a large difference in the future leak potential. Was the well cable tool or rotary drilled? Rotary methods allow for better cement seal installation around the casings. Was a full casing program run into the well, or were temporary casing strings used during drilling and then pulled during completion, leaving mainly just the production string? Was the casing even cemented in the hole at all? What was the purpose of the well? Brine production or brine disposal wells quickly experienced corroded casing and tubing. These many times were operated until all strings had eaten through and they were unable to be reworked and returned to service. We use geologic drilling logs to determine other potential source formations for leakage based upon drillers' logs and tests. Many times, not all formation with shows were produced or sealed off properly. Another point in the risk analysis is how the well was plugged. What kind of plugging materials were used? Was the bore filled with fire clay, pit mud, field clay, rocks, or debris? Were the infamous cannonballs dropped on the casing seats for bridge plugs? Those are more or less a do not pass go, do not collect $200 scenario. Was any casing recovered from the bore? How did they do it? Was it through cable tool ripping, shooting with explosives, and were there multiple attempts before the pipe actually separated and was able to be pulled? And then what was the track record of the plugging contractors? Was the well plugged for scrap metal around the World War II timeframe? Moving the analysis to address any health hazards, what is the proximity of the well to any potential receptors? Was it drilled on the bank of a creek, within a wetland, or has the area since become developed and a residence been built nearby? Are there any impacts to soil or groundwater around the well bore? Has any free product weathered or still volatiles? What is the ratio of light end to longer chain petroleum compounds within that soil sample? Presence of lighter end quickly attenuating constituents may many times indicate fresh leakage is present. Is the well leaking any methane or gas to the surface? Methane studies can be used as a minimally invasive screening and prioritization tool. If casing strings are at surface and a cap or surface plug is present, they can be cold tapped to determine if any pressure or fluids are reaching the surface. Once all of the data is collected from either historical records or views, if available, and any field investigation efforts, what then are the highest risk wells to address first? There are those that are immediate safety or public health risk. There are those that are causing environmental impacts to the environment. And then there's environmental justice considerations of wells located within underserved communities. And then wells impacted by land use changes or likely future development in the area. Out of these categorized wells, you can determine which ones need immediate action based upon risk, ones that can be monitored and are not near a receptor, and ones that are suitable for other passive approaches, such as what Dr. Ulrich will discuss later. And finally, wells that appear to have a competent plug and require no further action. A successful P&A program involves more than just drilling. Landowner and community interface to handle private land relations, local knowledge, and stakeholder engagement along with legal representation to handle landowner negotiations and access agreements allowing work to be performed. Surveyors are needed to provide detailed plans for sites with complicated topography and/or permitting issues. GIS personnel are used to create maps and databases of well information and locations. Geophysics surveys are essential to determine wellbore locations where surface casing has been harvested. Subject matter experts are needed to perform risk analysis, data review, and determine priority wells. Any necessary hydrogeological investigations need drillers and geologists to accomplish. Many of these early era sites require a litany of federal, state, and local permits to complete the work, along with regulatory reporting and correspondence to the state oil and gas regulatory bodies. Health and safety representation to ensure the bits keep turning to the right and everyone goes home safely is key. Technical drilling knowledge and well site management to schedule equipment, crews, specialty service contractors, along with getting through any downhole issues encountered. Waste management to handle manifests, landfill volumes, drill cuttings, impacted fluids, and drilling mud disposal. And then facility demolition and decommissioning to remove any remaining production infrastructure. Many times pipelines left abandoned within the ground from early era wells still contain product, and large amounts of debris were left or buried on site. Finally, environmental remediation and restoration to address any soil and groundwater impacts stemming from historical operations or active leakages. Generally, there are three main abandonment scenarios. There's an orphan producing well, which the majority of the time was a well that was walked away from and left in as-is condition due to the company insolvency or owner death. These will likely have all the casing intact, along with having the pump, tubing, and rods installed. These likely will have been involved in compliance issues and/or production potential that has waned below a profitable margin. This is the traditional scenario when you think of a plug and abandonment, and generally has the lowest cost and complexity, yet involves a total depth plug. Then there's replugging for aquifer protection that involves the re-entry and abandonment of a well to prevent any leakage from reaching drinking water zones and surface soils. This requires a much shallower clean out and plug operation to several hundred feet below solid bedrock and cementing the surface with cables and pieces. This is the most feasible scenario for previously plugged early era wells and will be of a moderate cost. The deeper you go, the more issues you are likely to encounter, or depending on the debris used as plugging materials, may struggle to even get that far. Replugging for producing zone isolation is usually required for gas storage or secondary recovery efforts in depleted fields. As pressure will be pumped into the formation, and offset previously poorly plugged wells may need to be redone to prevent leakage issues. This involves plugging the well to total depth, isolating the target producing formation to seal potential reservoir leaks and withstand injection pressures. This will be the most expensive and time intensive of the replugs, as increased depth equals increased time, which translates to added dollars. Note that there can be several thousand feet worth of drilling difference between the two replugging scenarios depending on the geology of the well. Early era plugging methods were fairly unchanged and done with limited effort from the discovery days up until around the 1960s. Generally, these plugged wells, with most of the casing recovered or at least underwent recovery attempts for scrap metal or reuse, especially in the World War II era. Most of the bore plugs consisted of shoveling or dump bailing old drilling mud remains from the on-site buried pits into the bore. If the pit was too wet or underwater, many times field clay was brought in. Iron cannonballs or improvised debris bridges were dropped in the casing seats to keep any fill from subsiding. Wooden bridge plugs or repurposed cellar boards that were also driven downhole. Think of a square peg in a round hole that was beaten on it until it became round. Generally, these wells have no surface caps on the casing, if any surface casing was even left in the hole at all. More modern plug methods became prevalent in the 1970s and involves multiple spaced Class A or pure Portland cement plugs placed at strategic intervals, as shown in the diagram to the right. In these, generally only the production and possibly intermediate casing strings were removed to allow the cement plug to bond to the native bore walls, preventing any possible preferential pathways. More precise and less explosive methods of casing cutting were developed, and wireline testing equipment was used to determine the free point, or where the top of the annular sealing cement was. Generally, casing is very difficult to remove below this point as it is bonded to the bore. Purpose-built and drillable cement bridge plugs were used and developed and began to be used instead of improvised debris. And finally, steel welded caps were welded atop the surface casing that was left in the bore. Early era plugs are not always permanent or competent long-term, as the formations can undergo a natural pressure rebound once the large-scale removal of fluids cease. It can also take time for preferential pathways to develop all the way to the surface and prevent an issue. We have seen many wells leaking up the backside of the casing via an easier preferential pathway versus through the center of the well that is filled with heavy mud. Cement dumped downhole may not have hardened or was not enough to keep pressure at bay, and wormholes resulted. Also, brine fluids left within the bore or casing annuluses may corrode and cause perforation over time. Early era wells were mostly drilled without today's modern environmental considerations and protections, and many present challenges. Many early era and discovery area wells are undocumented, and very little, if any, information is known about them. Many times these wells were drilled on uniform spacing orders. These grid locations often place the wells within floodplains, wetland, and on the banks of rivers, as the wells were usually drilled at the nearest feasible location of the survey point. To access these sites today, we need a suite of permits to address these sites, ranging from Army Corps of Engineers, JPAs, state permits, and soil erosion permits, and so on. Early era wells were many times drilled on locations with small equipment or standard derricks, which required a much lesser footprint than today's service rigs with accompanying support equipment. Also, over the decades, locations have settled, become unmaintained, and are straight inaccessible without major construction, as the access roads and locations are impassable and overgrown. Frequently, this requires construction and temporary land balancing to create the pad. The sites also contain buried drilling mud and sludge pits that can remain very soft in high water table environments and need to be removed for pad stability. When dealing with a previously abandoned well, finding the original well can be a challenge, and survey locations often differ due to change in methods the well was drilled on a more favorable adjacent location. They can often differ by 150 to 200 feet or more. The surface casing many times is harvested to various depths and is not present to allow for quick magnetic location. If the bore was not fully mudded to surface as the casing was pulled or the mud had settled, the upper part of the bore can collapse with native soils and be almost indistinguishable until deeper depths. Land use and grading changes can obliterate many indicators of the location or the upper part of the bore itself. Preparing for re-entry can take depending on how the well was left. Conductor casing may need to be inserted into the wellbore or driven depending on the local geology and washout heaving sand potential of the upper bore. If casing is present with either a steel or cement cap, a cold tap must be performed to test for pressure or flammables before the cap can be cut off and the wellhead nippled up for necessary circulation control and blowout preventer equipment. The image on the upper right is a magnetometer survey of a wellbore with the upper 80 feet of casing been harvested, and the top 24 feet of the bore filled with rocks and timbers. We had to excavate below the obstructions to insert or join a conductor casing solidly into the original bore to allow for replug. With the many unknown downhole issues that can be experienced, access to a large variety of local tooling is essential to maintaining efficient and drilling and avoidable downtime. Various diameter drill bits, milling bits to switch when mud, cement, and/or metal is encountered. Sufficient lengths of tubing, a number of drill collars to adjust drilling stem weight, and subs for adapting various tooling are also essential. Various specialty tools such as magnets and fishing tools to remove debris, tubing, and casing, impression blocks to help determine downhole obstruction, and wireline services to run cement bond logs, downhole cameras, and casing cutting and perforation equipment. Debris in the wellbore of previously abandoned early era wells is very common. Many times old tools, scrap, cable, and other junk from locations were disposed of down the well. Improvised bridge plugs made from iron cannonballs, field stones, tree branches, cellar boards, steel cable, and burlap sacks were often tossed or driven downhole. Previous rework or P&A efforts could have lost bits, tubing, casing collars, or segmented joints. We plugged a well once. We were having issues drilling down the 8 5/8" casing past 200 feet. Impression blocks came back inconclusive, so the wellbore was circulated with fresh water and a camera was ran down the hole. We found a joint of 7" casing that had fallen from the bottom of the casing string during historical removal and had wedged diagonally within the bore. We ended up having to put on a smaller bit and trip through that joint to move forward with the P&A. Inconsistent hardnesses of cement are frequently encountered, along with sticky field clay that will ball up on the bit and stop progress. Re-entry of remaining downhole casing can be difficult, as casing was ripped and harvested during previous P&A attempts, oftentimes left the top mangled and is needed to mill the top opening to re-enter. Cable tool collar rippers were used to roll the top of the casing joint inwards to release the tapered threads from the collar. Pyrotechnic shooting of casing also occurred for the larger diameters with dynamite or nitroglycerin that left the top of the casing mangled. I have seen a well record plugging log state that the casing was shot with 7 sticks of dynamite, and had another where they lost a live 20-quart nitroglycerin shot downhole, ran some debris atop, and then performed another shot 50 foot above. Talk about an unusual hazard of reentry. Oftentimes, wells with brine corrosion issues left tubing and collapsing casing strings in the hole and just dumped in cement without attempting to pull any of it, which makes for a particularly expensive replug effort. Lost circulation is a common problem and must have various loss-combating mud additives and access to additional fluids to replenish the pits. There can be single or multiple uncased or open zones of the bore that allow heaving and sloughing sands to enter and circulation to be lost. In these instances, sometimes a temporary string of casing must be ran down the well to keep the bore open and later pulled once the lower plug has been set. Parsons is modernizing the location and prioritization of wells by utilizing drone-based survey methods and remote sensing to locate well bores and determine those leaking methane that should be prioritized. We use magnetometers on drones to map areas and locate undocumented well bores along with those difficult wells where surface casing has been pulled. We use LiDAR to perform topographic surveys and identify former access roads, pipeline sludge pits, and former tank battery berms. The associated tank storage sites were often undocumented as to their exact location. Methane leak detection to identify and quantify wells leaking to surface and/or preferential pathways. This can also be used on operating infrastructure to safely find leaks around tanks, vents, and improperly burning flare stacks. We are also a technology company and are developing machine learning and AI systems to improve and speed up the risk analysis process. This will quickly and efficiently perform entry of critical data from historical forms used to determine the level of integrity of a previous abandonment. We use the intelligence systems to quickly identify and flag potential priority wells based on available data that would require further investigation. And finally, we interface this data with GIS systems to provide intuitive management of all the associated data layers. And with that, I turn it over to Dr. Ulrich.
Great. Thank you very much, Ron, and nice to meet everyone. Well, as Ron indicated, we have over 900,000 orphaned wells in the United States alone. And although our plugging capabilities and methodologies have improved substantially over the early era times, as Ron indicated, plugging remains to be the only technology that we have to address this very large and challenging problem. To that end, Parsons has been working with one of our clients for several years to develop a risk-based approach to manage their wells that are leaking, specifically methane. All of the wells in the study have been previously plugged and abandoned and subsequently determined to be leaking methane. Many of the wells are located in very remote areas and many times are heavily wooded, as shown in the photograph here in the bottom left. Our overall approach has been to quantify the rate of methane emissions in the vicinity of these wells, to identify factors that are controlling the rate of methane emissions in the vicinity of the wells. In addition, we evaluate the potential influence of these leaks on the vegetation and the surrounding shallow groundwater. And the focus of the next several slides is the work that we're doing to evaluate if methane is biodegrading in the unsaturated zone in the vicinity of these wells. And additionally, we have determined many of the factors that are controlling that natural methane biodegradation. This slide shares some details on our methodologies. There are 2 wells that were left cut and capped below grade. These wells were cut and capped at a depth of 2 meters below grade. 6 of these well sites were converted to what we call vent sites. An example is shown on the bottom left figure here, where you can see a wellhead and a vent pipe that is venting the natural gas 2 meters below grade to mimic a cut and capped well below grade. The advantage of this approach is that we can quantify the rate that the natural gas is being emitted into the shallow subsurface. As I mentioned, we do monitor groundwater. You can see a monitoring well here in the photograph on the right. We evaluate water levels, dissolved methane concentrations, and the potential influence of dissolved methane on the redox geochemistry. We evaluate the influence of vegetation on potential influence of these leaks on vegetation, including using drones. A significant amount of our work, and I should mention this has been ongoing for the past 6 years. And given all of these, the 8 different sites, we've generated a very large amount of information, including the distribution and concentrations of ADOS gases, including methane, CO2, and oxygen in the vicinity of the wells. The layout of the shallow gas monitoring probes is shown here on the right. Again, we measure and quantify the emissions of methane as well as CO2 in the vicinity of these wells using a variety of methods. We have a weather station. You see the weather station here that is evaluating meteorological conditions. We also have at 2 sites continuously monitor the soil moisture and temperature at 2 of the sites. This slide provides a brief background on methane biodegradation. And specifically, we are interested in evaluating the aerobic biodegradation of methane, where in the presence of oxygen, the methane is biodegraded by bacteria called methanotrophs to carbon dioxide, water, and there is some heat generated in the process. And importantly, the CO2 that is generated has a substantially lower greenhouse gas potential relative to methane. What that means is that if we could show that methane is biodegrading in the vicinity of these wells, and that process is significantly decreasing the flux of methane to the atmosphere, and that we understand the variables and conditions that are controlling that process, methane biodegradation could be a key piece of a natural methane attenuation management approach. Early on in the program, we identified spatial programs in shallow soil gas concentrations that were indicative of methane biodegradation. The upper left-hand figure shows the distribution of methane being highly localized to the well. That's a typical pattern. You see some slight depression of oxygen in the vicinity of the well. And importantly, we see an increasing concentrations of CO2 moving away from the well. The reason the CO2 concentrations are increasing away from that well is the methane is biodegrading to CO2 as the methane is traveling away from the well. We know that this predominant source of CO2 in the vicinity of these wells is the biodegradation of methane. An example of how we know that is shown in the green bars on the upper left slide or figure, showing the high concentrations of CO2 here in the shallow soil gas monitoring probes relative to the gas that's venting, very low concentration of CO2, and relative to the probes that are located far from the wells. We've developed multiple tools and lines of evidence that methane is biodegrading around these wells, including using carbon isotope ratios. An example of the data set is shown in the figure on the right. Methanotrophic bacteria preferentially biodegrade isotopically light methane, and that leaves isotopically heavy methane behind. So in this figure, we can see in the direction of the arrow, essentially moving up on the y-axis, an enrichment in C13 or isotopically heavy methane as that methane is degraded. we also see that that's associated with an increasing concentration of CO2. That's a clear pattern and a conclusive pattern indicating that the methane is degrading. But we need more than that. We need to better understand and be able to quantify the extent to which the methane is degrading at these well sites. And we've developed multiple methods to do that. And we have determined that in many cases, the extent of methane biodegradation is substantial, including in many cases, all of the methane is degraded. However, in other cases, the methane biodegradation is less effective. And we do see some temporal variability in the extent of methane biodegradation. And an example of that variability over time is shown in this slide. The left-hand figure shows the concentration of methane on the y-axis with distance moving away from the well. This data was collected over 4 periods of time in 2018. And we can see that in the summer months, the methane is not traveling greater than 2 meters from the well. However, in March of 2018, we see significantly higher concentrations of methane in that the methane has traveled a greater distance from the well. And interestingly, if you focus on the graph on the right, we see that the March time period is associated with very low concentrations of CO2. And this is indicating that the lower rates of methane biodegradation in March of 2018 resulted in increased transport of methane from the well. With a substantial body of information on variables controlling the flux of methane from these wells and factors controlling methane biodegradation, and this is just one of them. Shift gears to the work that Parsons has been doing for the past several years developing methane biofilters. An example of how we could apply a methane biofilter around a leaking well is shown on the right-hand portion of this figure. In this case, we have a well that is leaking below grade. That well could either be leaking naturally, it may have been capped or not. And in some cases, we could cut that well intentionally below grade and intercept the methane with a methane biofilter that converts that methane to CO2, water, and some heat. Again, the idea is that, and importantly, that CO2 has a 30 to 80 times lower greenhouse gas potential relative to CO2. The benefits of this methane biofilter technology is it would provide another tool in our toolbox. Currently, we don't have a toolbox, we have one tool. In addition, these methane biofilters could be installed at wells in very remote areas with smaller equipment and would result in significantly less disturbance to land. And additionally, through our cost analysis, we've determined that these methane biofilters can be installed for significantly lower cost relative to plugging. We're not saying that this is a substitute for plugging, but there are several wells, including wells that are leaking only methane, or wells that just won't be plugged in a timely manner, given the number of wells that are leaking methane. So I'll shift to some of the results from our laboratory work. This slide, I'll pause a minute because I know there's a little bit of a delay here in the slides. This slide shows the work that we're doing in the laboratory to evaluate methane biodegradation and developing our various methane biofilter matrices. You can see in the upper left-hand slide, 2 sets of experiments where we're evaluating methane degradation and sustainability in methane degradation using static bottle tests. We can do this very quickly. In addition, on the right, you can see a flow-through column test where we've evaluated methane biodegradation with a biofilter matrix. To this point, we have evaluated at least 50 different types of biofilter matrices. This slide outlines some of the factors and considerations in really what's dictating what we've tested to this point. The overall goal of these methane biofilters is to sustain methane biodegradation for very long periods of time with limited or no intervention. We know that that's a key aspect of this technology if it were to be widely adopted and applicable over a large scale. That means we need to be able to control the microbial environment to sustain methane degradation. In the laboratory, we have evaluated different sources of methanotropes. Again, methanotropes being the bacteria, aerobic bacteria that degrade methane. We have evaluated a variety of nutrients and different methods to apply these nutrients to maintain their availability over time. We have evaluated matrices that retain moisture, which is a critical aspect of sustaining methane biodegradation. Again, these are going to be out in Mother Nature under a variety of conditions. We have evaluated different materials that enhance the porosity and assure methane migration in contact with the biofilter materials, and we have evaluated the retention of methane in these biofilters. And finally, we have evaluated materials that we can add to maintain the pH. The constructability and cost was a key consideration in our work. And this includes that we know that the methane biodegradation rate needs to be significant for these biofilters to be applicable. And we can say that for sure we see substantial rates of degradation that can intercept methane from wells that are leaking methane based on published rates of methane releases and the rates that we see as well at our sites. We have evaluated only low cost and readily available materials. And finally, just to make this point again, that an advantage of the methane biofilter technology is we can apply these methane biofilters using methods that avoid the use of heavy equipment. An example of the laboratory results, in this case static bottle testing, is shown in this figure, where we see no methane degradation, where in samples acquired from a landfill that was leaking methane, both with and without nutrients. However, when we create a methane biofilter using that soil, we see effective methane biodegradation over time. Interestingly, we typically see an increasing rate of methane biodegradation after we respike the methane. And that's indicating that the methanotropes have grown, yielding a higher rate of methane degradation. This slide shows results from testing, evaluating methane biofilter matrix performance under wet conditions. So for example, after a heavy rainfall. And we can see that depending on how we construct the methane biofilter, we see different rates of methane biodegradation. And finally, these results show examples of where we have stimulated methane biodegradation using different types of nutrients. We recognize that methane biofilters could be applied not only to oil and gas wells, but other point sources of methane, such as mines, which is a substantial source of methane within the United States. And we also recognize that work has already been done at landfills to evaluate methane biofilters, predominantly in the laboratory. The distinct difference between that work and the work that and the biofilters that we're developing at Parsons is those filters are generally comprised of readily decayable material that will decompose over time. So a few brief conclusions. I think Ron did a great job to show that experience, understanding, and more than just concrete and a drilling contractor are critical for a successful plugging program. He showed that technical expertise is required to locate wells and resolve several downhole challenges. In addition, Ron shared that early era plugging wells, such as cannonballs, were not the best approach, but that Today, the approach for plugging wells has greatly improved and continues to improve. Despite those improvements, and knowing that plugging is a viable alternative, it's a proven technology. However, it remains to be the only technology that we have to address this problem. To that end, Parsons has been working with one of our clients for several years. We're continuing this work to evaluate a passive methane biodegradation and attenuation approach for their wells that are leaking methane. To this point, the results indicate that that is a viable technology, and we continue to work with our client and the regulator on that project. Importantly, we've demonstrated that the aerobic biodegradation of methane is occurring and can be significant, thus limiting the extent of methane emissions to the atmosphere and reducing the greenhouse gas potential. Parsons has been working hard to develop methane biofilters that stimulate and sustain methane biodegradation, and we're excited. We think that this is a viable alternative for some wells, such as wells that are leaking only methane and wells that can't be plugged in a timely manner. In addition, these biofilters can be applied at a much lower cost, including at locations where that are very remote, thus making that technology more applicable for remote locations, thereby reducing impacts to surface ecosystems. The next step for methane biofilter technology is really to push this into the field. We do have one pilot test planned for this spring, and we are interested in working with additional partners to push this technology into the field. And with that, Ron and I would be happy to take any questions that you may have. Thank you.
Thanks, Ron and Glenn. That was a really interesting presentation on all the issues and challenges of abandoned wells, and also some improved approaches to how to address them. So thank you both of you for your presentation. If there are any questions, you can either raise your hand and we will call on you, or you can enter your question into the chat and we'll read it off. So the first question we have is from Matt Colbert. Is there a correlation between the boring diameter thickness and costly or difficult plugging? And are there any abandoned well attributes that would suggest a well can't be plugged, for example, below the water table, but where methane biofilters may be a viable alternative? So maybe let's take the first part of that first. And is there any correlation between boring diameter thickness and costly or difficult plugging?
Not necessarily. Where things get costly is more or less of how was the well left, and is there going to be any obstructions that'll slow you down. We've had 5-inch casing that's just as hard to clean out and get to the bottom of as 10 or 14-inch casing. The only cost difference there is going to be the just volumes of cement used to plug that larger diameter casing.
Okay, great. And then the second part was, are there any attributes that would prevent a well from being plugged, or where methane biofilters would be a viable alternative?
Yes, there are always certain things that were done back in history that can prevent a well from being properly plugged or plugged as deep as you want it. If when you're re-entering it, tooling gets stuck, or you're able to, with heaving sand or collapsing bore because of the lack of casing, that can certainly make it issues. Or as I mentioned, the cannonballs being dropped down hole. Those are very difficult and very expensive to try and either recover from the hole or drill through. Most of the time, that's about as deep as you're going to cost effectively go, is wherever one of those is set.
Okay, Glenn, I don't know if you had anything to add on the biofilter portion.
I guess I don't see any reason that a methane biofilter couldn't be applied under the scenarios that Ron just mentioned. Some of the conditions that would favor the use of an application of a methane biofilter would be the scenarios where the predominant risk is methane itself. So I think that would be the primary criteria. In addition, you know, if there's going to be some time before these wells can be plugged, regardless of whether they can be plugged or not. You know, one idea that we have is that the biofilters could be an interim measure for those leaks.
Okay, great. I see you here, Chokshi, you have your hand raised. If you can unmute yourself and ask your question.
Sure, thanks, Jess. So I have a two-part question. One is, have you guys worked with regulators in terms of your risk-based methane management? I.e., what's your acceptance experience with regulators? And two is, if you can give a flavor on cost differential between a traditional plugging well, you know, 2,000, 3,000 foot plug well versus a methane biofilter application.
Great questions here. We are working with the regulatory agency on that risk-based methane management project. They approve the work that we do for the purpose of gathering information on the applicability of the approach. And in terms of the cost to install biofilters, I think was your second question. Yes, we've determined that installing methane biofilters can be installed at significantly lower cost relative to conventional plugging.
Thank you.
We have another question in the chat from Daniel Siegel. How would methane biofilters be installed in the field? VADOS or saturated zone? And what about groundwater quality impacts from methane?
Yeah, I think those are both good questions. Methane biofilters would be installed in the unsaturated zone. And, you know, from there can be impacts of methane on groundwater quality. Generally, they're secondary impacts, such as increased iron concentrations. But methane itself is not toxic. And from what we're seeing at our study site, we're not seeing a lot of impact on the groundwater. But of course, you know, sampling groundwater and assuring that there's not a significant impact would be important. But from what we've seen and what we know about how methane can influence groundwater, I don't see it as being a reason to not go with the methane biofilter technology, because those risks and impacts are overall relatively small.
Todd France, you have your hand raised. You can go ahead and mute yourself and ask your question, please.
Yes, thanks, Jess. So I understand, you know, methane, you know, leaks are bad, obviously, and we have can do risk-based prioritization to address them. But I guess, are there regulatory thresholds or limits that, you know, many states or the EPA has to determine, how much methane is too much, kind of thing? And how long does it take to do an assessment once you figure out that, you identify a well and it might be leaking methane? Is this something you can do in a day, or is it like weeks, or how long does that process take to figure out what's being emitted and what you need to do about it?
Oh, those are good questions, Todd. In terms of the latter question, it's pretty, it depends on the tool. If you just want to know if there's a leak or not, that can be done with ground-based tools very quickly. There's some work developing aerial methods as well. But yeah, you can determine if a well is leaking methane very quickly. There are strict regulations, including in Canada, where methane leaks would prompt plugging the wells. In the United States, there's more of a state-by-state thresholds. So I think hopefully that answered your question, both your questions, Todd.
Sure. So it sounds like states do have specific values as to I guess it's the quantity of methane being emitted over time kind of thresholds.
I don't know that states have a threshold. I don't think there's a threshold, published threshold. Jessica, help me out
Okay.
here. Yeah, I don't think the states have, or US state, nationally, there are, standards for rates of methane release that are acceptable versus not. Is that correct, Jessica?
Yeah, it's a state by state basis. So, and we expect to be some, progression and changes with how states approach methane, in part because of the bipartisan infrastructure law and the increasing focus on reducing methane emissions, especially with, these abandoned wells.
Great, thank you.
If there are any more questions, feel free to put it in the chat and we can read it out, or you can raise your hand and we'll call on you. We've got a few more minutes if there are any more questions still. I guess in the meantime, we can go to the next slide. So next month's webinar will be on August 10th at the same time, 12:30 p.m. Eastern, and we will be presented by Mike Nahir and Les Cordone on mining environmental management, Parsons best practices applied. So we hope you can join us next month for that and see some of the work we've been up to. If there's no more questions, we can, I guess it's the final call. If you have any issues downloading the PDH form and you wanted to get credit for today's attendance, please let me or Daniela know at daniela.savin@parsons.com. We can get you that form. So I think that's all. And so thank you to everyone again for joining us today for today's webinar, and we really hope to see you again next month.